January 5, 1943. Allied anti-aircraft guns suddenly turned lethal. Bombers shattered in midair. But before that winter, the geopolitical might of global air defense hung on one primitive detail: a tiny brass clockwork. Why did heavy shells rarely reach their target? A mechanical timer required a perfect calculation of the time to explosion. Logistics networks transported heavy munitions empty. Safety came first. Crews armed the payloads right on the firing line. An artilleryman grabbed the brass cylinder. He threaded it deep into the steel nose of the shell. A specialized wrench turned the dial. A sharp metallic click locked the mechanism. Operators set these mechanical time fuses anywhere from 0 to 30 seconds. Field cannons utilized basic point detonating fuses to crush infantry trenches on impact. But the sky offered no walls. The sky required math. Global empires built colossal industrial chains to defend their airspace. Factories cast millions of shells, while logistics drained massive national resources. Yet this entire macro-level war machine crashed into a micro-level bottleneck. Heavy 90mm guns launched steel at 800 meters per second. Human crews had to predict the exact intersection point manually. An impossible task. Destroying a high-altitude bomber became pure statistical luck. A manual calculation error of just 1/10 of a second threw the explosion 80 meters wide. To counter this statistical nightmare, states built sprawling complexes just to mask a tiny mechanical flaw. The German 88mm FLAK cannons became the backbone of this desperate math. Würzburg radar dishes swept the dark sky. Thick cables fed raw data into a central mechanical computer. Inside the bunker, gears turned. The machine crunched altitude, speed, and course. Firing solutions transmitted outward in real time. Crews on batteries of 4 to 8 guns synchronized their dials. Loaders shoved heavy steel into the breeches. Automatic setters locked the timers. The fire order dropped. A deafening, synchronous roar shattered the night. The ground violently shook beneath the heavy mounts. Black clouds of shrapnel ripped through the cold air. But the fuses remained inherently imprecise. The state had to choose volume over accuracy. Bringing down a single bomber consumed an average of 3,000 shells. 3,000 rounds equaled nearly 30 tons of high-grade steel, brass, and explosives. Feeding this insatiable artillery network bled the German war machine dry. The logistical weight of manufacturing and transporting these massive stockpiles crippled the Reich's industry faster than the Allied bombs falling from above. Entire factories worked exclusively to supply a blind barrage. Every trigger pull was a gamble against an empty sky. The gunners aimed at blank space, predicting a future impact point. The projectile's flight to a high-altitude target lasted up to 20 seconds, but anti-aircraft guns, burning thousands of shells in the sky, were just one branch of a giant artillery conveyor. Why did states build monsters of 800 millimeters? The rapid evolution of weapons demanded increasingly heavier shells from the industry. Nations poured their economic might into specialized branches. Field guns delivered direct fire. Howitzers threw heavy steel beyond the line of sight. Infantry hauled light mortars. Commanders measured the true industrial race in barrel width. Factories stamped out millions of steel tubes. Standard calibers ranged from 20 to 155 millimeters. Then came the anomalies. The Schwerer Gustav, an 800-millimeter railgun. Maintaining this single weapon required a dedicated railway infrastructure and a crew of several thousand men. It demonstrated a colossal but largely inefficient allocation of state resources in the global industrial race. Calibers evolved rapidly. State industries pushed barrel dimensions all the way up to 800 millimeters. Yet the basic mechanical principle of the guns remained entirely unchanged. They operated exactly like simple, upscaled steel pipes. The real difference lay inside the ammunition. High explosive shells dominated the massive supply chains, millions of them. Assembly lines also churned out shrapnel, armor-piercing, and smoke rounds. Commanders easily bypassed the rules of war at the factory level. The Japanese army fired lethal chemical payloads disguised as standard smoke shells. During the First World War, artillery caused 75% of all casualties. By the outbreak of the next global conflict, nothing had fundamentally shifted. All this industrial might, from 20mm anti-aircraft guns to 800mm behemoths, strictly followed the rules of the trench era. What did the primary striking force of the armies rely on? Manual calculations, paper maps, and wired telephones. The doctrine of the 1930s treated heavy guns as the undisputed king of the battlefield. Generals built their strategy on three rigid pillars: counter-battery fire to blind the enemy, interdiction to sever rear supply lines, and direct infantry support. The principles were solid, the execution remained archaic. State economies churned out millions of shells, but guiding them to the target required a game of blind guessing. Gunners fired a massive salvo at approximate coordinates. Then they waited. The dry rustle of paper maps and the creak of wooden rulers filled the artillery command posts. Spotters in the mud dictated adjustments through fragile telephone wires. Human brains crunched the numbers. Human hands adjusted the heavy steel barrels. Armies unleashed days-long bombardments and sheer mass to compensate for terrible accuracy. The global race for heavier calibers collided with a severe bottleneck. A factory could forge a flawless howitzer in hours, but a forward observer still needed precious minutes to calculate the wind. This manual doctrine had reached its limit. To shatter the limits of manual calculation, Allied engineers integrated a revolutionary sensor directly into an artillery shell. They stamped the metal casing with two letters, VT, variable time. The official marking masked the device as an ordinary timer. But beneath the steel cap hid a fully functional miniature radar. How to preserve battery charge during long storage in warehouses. Engineers sealed the electrolyte inside an airtight glass ampule. It kept the corrosive fluid strictly isolated from the electrodes, safe and dry, until the exact fraction of a second when the gun fired. The colossal pressure of the powder gases slammed into the shell base. The glass ampule shattered with a violent, sharp crunch. Acid flooded the chamber. The wet battery instantly sparked to life. It fed power directly to the miniature radar. The shell cleared the barrel, broadcasting a continuous stream of radio waves into the clouds. It bounced signals off enemy bombers. The detonator triggered the millisecond the echo reached maximum strength. But combat always meant missing, and a dud shell dropping into enemy territory posed an unacceptable strategic threat. The United States government protected the VT fuse technology with the exact same ruthless paranoia as the Manhattan Project. This single piece of hardware guaranteed Allied geopolitical supremacy in the air. German engineers could never examine an intact specimen, so the designers installed a mandatory failsafe, a self-destruct mechanism. If the radar found absolutely nothing in its path, a backup circuit bypassed the sensor. The internal explosive ripped the stray casing into jagged shrapnel, high across the empty sky. For the secret radar to function in combat, its internal components had to survive the brutal physics of an artillery launch. 20,000 Gs. That was the acceleration slamming into fragile radio tubes upon exiting a rifled barrel. This force exceeds the lethal human limit by hundreds of times. A pilot would be pulverized instantly. Yet microscopic glass had to endure. Inside the steel nose cone sat a delicate transmitter, an amplifier, and a trigger mechanism. The centrifugal spin threatened to shred them all. Engineers needed a rugged solution to enable mass production. They found it in basic chemistry. Technicians potted the entire electronic assembly in dense resin and wax. The hardened compound locked the vacuum tube safely in place during violent flight. Early trials proved chaotic. The sensitive radar triggered on ocean waves. It even detonated near passing seabirds. But by mid-1942, the industrial barrier finally fell. The design was stabilized. Factories immediately rolled out the technology for heavy naval guns. The geopolitical advantage was absolute. Combat records soon confirmed the exact tactical leap. The new proximity fuses delivered a kill rate over 50% higher than traditional time-fused shells. That 50% leap in 1942 did not start on American assembly lines. It originated 2 years earlier on British drafting boards. In 1940, Great Britain conceptualized a radical shift in anti-aircraft warfare. Why did Britain transfer this project across the ocean? American industry possessed the resources to realize an impossible idea. The rustle of top-secret blueprints crossing the Atlantic in diplomatic briefcases marked a definitive strategic merger. British scientists designed the initial radio circuits. The United States provided the industrial scale to mass-produce them. Two global powers fused their survival strategies to dominate the airspace. American military engineers immediately locked the foreign schematics inside secure vaults. The underlying logic was flawless. Radio waves could trigger a shell precisely near an enemy bomber, completely eliminating the need for inaccurate manual time fuses. The concept worked perfectly on paper, but theory is weightless. The problem was the dimensions. Those 1940 British blueprints became a geopolitical lifeline. Across the Pacific, traditional American naval artillery was collapsing. The Navy met the crisis with brute force. Heavy Iowa-class battleships transformed into steel fortresses. 20 quadruple 40mm Bofors mounts densely covered the deck of a single vessel. The deafening roar of a simultaneous salvo shook the hull. Tons of hot metal tore into the sky every minute. How do you stop a swarm of planes unpredictably changing altitude? The fleet had to literally flood the sky with lead. Japanese pilots adapted. They executed high-speed dives. They skimmed the ocean surface. The kamikaze threat stripped away any margin for error. A battleship spewed curtains of metal from dozens of barrels. But the enemy planes twisted unpredictably. They slipped right through the black clouds of FLAK. 20 and 40mm impact fuses demanded a direct physical strike. The misses accumulated. One surviving aircraft, loaded with explosives, sank thousands of tons of Allied armor. The fleet relied heavily on their 5-inch anti-aircraft guns. Radars pinged incoming squadrons. Fire control systems fed data to the turrets. Crews fired 55-pound shells equipped with mechanical timer fuses. But Japanese aviators learned to break their flight paths. The shells detonated harmlessly high above, or they detonated uselessly below. This systemic inaccuracy paralyzed the macro-level logistics. Expending thousands of heavy 55-pound shells on a single plane crushed the Pacific Fleet supply lines. Cargo ships could not haul ammunition across the ocean fast enough. A prolonged maritime defense became an industrial impossibility. Brute force failed. Downing one enemy plane required 2,500 shots. By late 1944, in the Ardennes forests, 200,000 secret artillery shells rewrote the rules of ground warfare. The Battle of the Bulge broke out. Over 400,000 German troops surged forward. Thick winter fog swallowed the landscape. It masked the valleys. It completely blinded Allied ground spotters. How do you stop a massive offensive when the enemy is securely hidden by heavy fog? You change the ammunition. Supply trucks rushed the new VT shells directly to the frontline batteries. The wooden crates carried no standard labels, just a classified cipher stenciled in black paint across the lids. 200,000 rounds waiting in the snow. The batteries opened fire. A shell arcs toward the front line. It does not bite into the frozen earth. It freezes mid-air. 50 feet above the German positions, the proximity fuse triggers. The shell transforms into a lethal dome of steel fragments. Shrapnel shreds straight down. It instantly blankets the hiding infantry. Trenches lost their tactical meaning. An open foxhole became a mass grave. Stripping away the landscape's physical protection instantly nullified the German numerical advantage on the ground. Infantry columns marching blindly through the fog took catastrophic losses in the open. The technology rendered the terrain useless. Frontline dispatches reached German high command. The intelligence reports documented a sudden, inexplicable surge in Allied artillery lethality. They confirmed that standard defensive earthworks no longer provided basic survival guarantees. Anti-aircraft effectiveness suddenly multiplied 50 times. But before General Eisenhower secured these fuses for land combat, the military restricted the technology exclusively to the ocean for 2 years. British coastal batteries reported an 80% increase in hits against German bombers and V-1 flying bombs. Total paranoia dictated the rules. Washington guarded the proximity fuse exactly like the atomic bomb. A single intact shell falling into enemy hands meant disaster. On land, enemy scientists could dismantle a dud. Over water, duds simply sank. The cruiser USS Helena demonstrated this naval supremacy. On the 5th of January 1943, its 5-inch guns fired the new fuses in combat. The blast instantly shredded a Japanese bomber. The mathematics of warfare shifted. Gunners dropped ammunition consumption from several thousand shells down to 150 rounds per kill. This exact metric changed the geopolitical map. The plunge in ammunition usage radically unloaded logistical supply ships. The United States Pacific Fleet gained unprecedented strategic autonomy. Task forces stayed at sea longer. They struck further. The ocean perfectly concealed the ultimate weapon. General Eisenhower explicitly demanded the immediate removal of all restrictions for ground operations by the end of 1944. The massive deployment of detonators across the Ardennes and the Pacific Fleet required unprecedented mobilization. American industry had to deliver 22 million VT fuses. But where do you find the manufacturing capacity to produce millions of complex radio components during a total wartime deficit? You draft the civilian sector. Assembly lines pivoted overnight. Workers traded festive ornaments for the fragile glass of tiny radio tubes. Christmas lights factories were quietly absorbed by the military-industrial complex. Strict state secrecy locked down the production floors. The shift left a visible mark on the home front. At the height of the conflict, decorative holiday lights completely vanished from American store shelves. They could not be bought anywhere. The state transformed a peaceful industry into a lethal pipeline, hiding the most advanced anti-aircraft technology in plain sight. Axis intelligence realized the threat. They hunted for the secret, tearing their squadrons from the sky. They desperately needed a physical sample to copy. But the designers anticipated this geopolitical espionage. A built-in self-destruction feature ensured that any shell missing its target detonated before hitting the ground. There were no intact duds. The Allies fired thousands of rounds, leaving nothing behind for enemy engineers to scavenge. The technological quarantine held. The espionage failed. The total number of proximity fuses successfully reverse-engineered and mass-produced by the Axis powers remained absolute: 0.